I hope you're all having a great day. I'm Mr. Ish. Thank you for joining me. If supposedly we were tasked with perhaps verifying that the area of that circle is pi r square, and to verify it, is there a way to verify it? Perhaps utilizing some ingenuity, some approximation, all of that. And the answer would be yes. The best you can do without getting into calculus would be good approximation. And that good approximation or a good level of approximation is what we would do in this particular video, and we can get a formula close to pi r square. How would you go about doing it? X squared plus y squared equals r squared, and you know what that formula is. That formula is the equation of a circle on a xy axis. You know that. X and y axis, x squared plus y squared is equal to r squared. And what's the radius over here? The radius is just r, right over here. You know you would have a coordinate here, r comma 0, and here you'd have a coordinate minus r comma 0. If you were to take this specific equation right here, the unit circle equation, and you solve for y squared is equal to r squared minus x squared, y is equal to square root of r squared minus x squared. And if you were to look and focus only on that equation, what would happen is, because you have a radical involved, you cannot generate a negative output in terms of y. All the values you put in here should always be 0 or positive, because you can't do a radical of a negative number. You can't do square root of negative. So what would happen is your entire graph would become this. You would be looking at a half a circle, hemicircle, semicircle, and that would be the equation of this graph right over here. What you can do by means of approximation, if you can squeeze in rectangles, the more you squeeze, the more accurate. But given the fact that we're doing a video, we have space, time, all of that limitations, we have to be reasonable in our approximations. If you were to squeeze in just 4 rectangles, but the more you squeeze in, the closer you would get to verifying that formula. If you put like only 1 or 2 rectangles in here, you'd have a formula which would not be accurate. But if you can do at least 4, it would be quite accurate. You see, I've drawn 4 rectangles. Each of these rectangles, if I just pluck out one, it has a certain width and a certain height, or a certain length, W and L. If you do L times W, you know you're getting area of this rectangle. If you calculate the area of this rectangle, this, and this, and you add them up, you should get an area of half a circle. But to get the rest of that circle, because we're looking here at a radical, you just multiply your end answer with 2, and you would get the area of the full circle, and that would be the means by which you would verify this pi r square. And the method of approximation is not bad. It's a technique you learn in the beginning of calculus. It does not require you to understand calculus, but it's a means for you to understand calculus. You see the difference in that? And you can do this technique of approximation by a table. You can have a table here with interval. You can have a table here with your points. These are my selected points, and then you can have an interval here representing the length of each of these rectangles. I have 4 rectangles, therefore I have 4 intervals, 1, 2, 3, 4. But what exactly are the intervals? If I am looking at everything here from minus r to r, remember on the x dimension, minus r to r, and I have 4 of these. If I did the distance between these two, and I can do r minus r, r minus r, just the distance of this segment, and I divide them by the number of rectangles, which are 4. I have 2r over 4 and then r over 2. This r over 2 would represent the width of each of these rectangles, but this r over 2 would also represent each of these intervals. If you're starting here from minus r, the next one would be r over 2, minus r over 2, minus r to minus r over 2. Then the next one would be minus r over 2 to 0, minus r over 2 to 0. And then lastly, it would be 0 to r over 2, 0 to r over 2, and then r over 2 to r. And the benefit of all of this is it's an even function. This right here is even function, is symmetric about axis on the right and the axis on the left. It's symmetric on both sides. You could technically just focus on 2 of these and multiply everything by 2. Everything would be mirrored. But what points do you want to use? Generally, when you're doing these, you want to use the midpoints of your interval. If I do minus 1 and minus 1 over 2, or minus r and minus r over 2, what's the midpoint? That's like doing minus 1 and minus half, you get minus 3/4. So it'd be minus 3r over 4. But exactly, it's even function, everything mirrors. If this is minus 3r over 4, this would be 3r over 4, because everything is mirrored right and left, symmetry around the y-axis. What's the middle of minus r over 2 and 0? It would be minus r over 4. It's the same thing as you doing the midpoint of minus half and a 0, it would be minus 1/4. and of course this would mirror it because of the y-axis symmetry, even function all the way. Now what would you do over here to determine your length? We've already determined the width. Right here is my width. The length is exactly this right here. You would put everything here in terms of these x values right in here. You would have r square minus this square. You're doing 3r over 4 squared because these represent your x values. It would become 9r squared over 16. But exactly what you see over here would be exactly what you would have over here because of that y-axis symmetry, and you will see that to come true. Minus r over 4 and r over 4 will have exactly the same because these are representing the lengths of these rectangles. Two of these rectangles are short, two are long, but in width they're all the same. Here you'll have a r square minus r square over 16 because you're putting this r over 4 plus or minus right here in place of x. Here you'll have an r square minus r square over 16, but you can simplify each of these. If you do a common denominator right here in this radical, r square minus 9r square over 16, common denominator of 16, you'll have 16r square minus 9r square over 16, which would be a square root of 7r square over 16. Think about it. This is r square over 1, common denominator, 16. That 1 goes in 16 times. You have 16r square minus 9r square, which is 7r square over 16. And the answer over here would still be the same, 7r square over 16. The answers for these two in terms of the lengths will be the same. Common denominator 16, r square minus r square over 16. You'll have 16r square minus r square. You'll have 15r square over 16. Here you'll again have 15r square over 16, and all of these are in roots. And again, you can simplify them once more because you have perfect squares showing up in here. This right here will simplify to r over 4 root 7. This is exactly the same. This right here will simplify to r over 4 root 15. You have 2r over 4 root 7s, which are these ones right over here, and you have 2r over 4 root 15s, which are these ones right over here. Because everything is doubled by means of that symmetry around the y-axis, even function right over here. Now you've gotten the lengths of each of these rectangles. Two of these rectangles are short, two of these rectangles are long. The short ones have this length, the long ones have that length. Add them up, multiply them by that width. You can do individually length times width plus length times width plus length times width plus length times width, or you can add all the lengths and multiply by the width once, and it would be just the same. Think about it. LW plus LW plus LW plus LW, and these are L1, L2, L3, L4 because the widths are all the same. Or you can isolate the W and do L1 plus L2 plus L3 plus L4, the lengths. Add up all the lengths and multiply the width ones, or do this individual computation. This way right here is easier and it's more efficient, and that's the way I'm going to do. Again, I have two of these, I have two of these. Because I have two of these, I have to multiply with that. Remember, I have two and I have two of each. But you can do simplification here. 2 times r over 4 root 15 is just r over 2, because the 2 and that 4 cancelled each other out. Same thing over here. Now this represents the cumulative lengths of all the 4 rectangles involved. Now let's create some space and get this area formula verified. And the space I'm going to create for you is right over here, because I don't need to see this representation anymore. You've seen it, and I'm going to erase this right here because you don't need to see it. I won't erase the table. I have this r over 2, which is my width outside. Then I have these, but this right here represents 2, this represents 2, because I already did the simplification. R over 2 root 15 plus r over 2 root 7. This represents 2 of the long rectangles added together. This represents 2 of the short rectangles added together, their lengths. Do the computation. And remember, we were looking at the very beginning at a semicircle. We have to do at the end multiply by 2 to get the lower part. Remember that? We have to capture the lower part. The radical only looked at the top. It never looked at the bottom. So I can do that multiplying by 2 right now, and I can capture that times 2 right over here. But since I've added this times 2, you see this 2 and this denominator 2, they can cancel out, and they will cancel out. When you cancel them out, this and this, you just have an r sitting outside. Here, you can do a common denominator. You have root 15 with an r plus root 7 with an r all over 2. You can bring this 2 right out here, and you can bring the r outside. You can bring the r's. You'll have a r times r over 2, and then you have a root 15 plus root 7. There's nothing here other than just algebraic simplification. That's it. I isolated this r from right here, brought it out, but I multiplied with this r, and there it is. I've taken this 2 out, I've isolated and I brought it out. I'm having an r squared over 2 and then root 15 plus root 7, and this right here is my area formula for that circle, and I will verify it with you right now momentarily with this. But remember at the beginning I said the more rectangles I draw, the more closer this formula will become to that formula. The fewer rectangles I draw, the further this area formula will be from that, because the more you draw, the more accurate you are in terms of approximating to the true area. We're right now only getting an approximate area, and approximated area is all we can do best utilizing this technique. Now look right here on the calculator, you have area is equal to pi r square. You know pi is 3.14159. This right here is really 3.14159 r square. I've just rewritten it here, eliminated the pi and brought in the actual numerical value of pi, 3.14159. If I do the numerical value of this and divide it by 2, I should have a value close to that, and we can show it to you. It'll be root 15 plus root 7. Now divide this by 2, I'm getting 3.259, and I'm going to bring the area formula right here. I'm getting here 3.25936 r squared. This is the area formula. I'm getting my approximated estimated area formula for a circle, but the true is right here, 3.14159. Why is this accurate over here and this is not as accurate? Because this was derived from the same procedure using an infinite number of rectangles and cumulatively adding their length and width, their areas all the way across to give you this. I only did 4 rectangles. Had I done 100 or 1,000 or 10,000 or whatever number, this 3.259 would slowly creep its way up close to 3.14159, and then this right here would slowly become pi r square. But again, I only used 4 rectangles, not an unlimited number, because I have space and I have time limits. And we did this all by means of estimation and approximation, and you know what that procedure was. We had a little equation here, we graphed it. We only had half of a circle, but we did 4 rectangles in it, and we sent the procedure through. We multiplied everything here by 2, as you remember, to capture the remaining of that semicircle which was not captured because of that radical. And that right there is the gist of this particular exercise. We have actually verified the circle area to be pi r square. If anyone asks you why the area of a circle is pi r square, the reason to that, or your answer to that, would be if you can squeeze in an unlimited or an infinite number of rectangles into a circle graph and you cumulatively add the areas of all of those rectangles, it will always add up to the 3.14159 r square in terms of that area. And that's it for this video. Thank you for watching. Have a great day. Bye.